And I want to remark, I am sure that someone said it before me, that 2025 is the International Year of Quantum Science and Technology, of course. And maybe I should first welcome everybody. Sorry, dear attendees, I'm very happy that I can be here, and I'm going to talk about quantum teleportation now. So at the beginning of the year, there was an opening ceremony for this year in Paris, and uh, they discussed on the second day the social impact of the new technology. So quantum technology, is it a threat or is it an opportunity? And why could it be a threat? Well, because it is costly to develop, and one could think that the nations that are not as rich as others kind of cannot do it, and then the others do it, and then the gap widens, right? So that's the threat. And why is it an opportunity? Because for the same reason, I think that we can use this as an opportunity to develop technology, new technology, in the end, a new industry, and with that industry we can develop. Okay, so new technology, new luck, and a new opportunity. Okay, and I think we have a lot of things going for us, but you will see that later. So how can we understand quantum technology? I want to try to explain it one more time. I'm sure the others did a fantastic job, but I also want to try to explain it. And then I will come to teleportation. So let's first look into quantum technology. What is it? It has three pillars: quantum sensing, imaging, the other one, quantum computing, and quantum communication. And I saw your program. All of these three pillars are covered fantastically. So this is really a good discussion forum. I want to take it from a different point of view. I want to explain to you first what information theory is, and then what quantum information theory is. What's the difference between the old information theory that was so successful and the new quantum information theory? So in the classical information theory, you always have a sender and you have a receiver. And the sender, you can guess it, sends a signal to the receiver. So this could be a radio wave. And then the question is always how much information is in the message that you send. So let's say you have three possible messages and three different probabilities with which you expect these messages. Then somehow the information content in information theory is quantified by thinking about the probability, not about the meaning of the message. This is a big step forward. Namely, if you get a message that comes always, so every day the same message, then you don't learn anything, and that means no information gain. While if you get a message that is not, that you don't suspect is one of many messages, and there is one that you don't suspect, then you learn something, and there is a lot of information content in that. So to give you a simple example, let's say I tell you, you won't win the lotto this week, then you will not be surprised. There is little information content in that. If I say you will win the lotto this week, then the surprise is big, of course, and you are rich. And it's a nice thing because there is a lot of information content in this. So the information that A contains, the message A, is the smaller the probability it is, the more information it contains. And we can quantify this now. So we say that the information content is a function of the probability. And one more thing we need, namely that the information content is additive. So if I send you message A and B, then you want to have the information content of A plus the information content of B. And the probability for A and B is the product of the probabilities if they are independent. So what function can we think of? First, you would maybe say, oh, maybe it's inverse proportional. So if I have a probability, then the information goes with 1 over the probability. But in order to get the second the second property right, you can use the logarithm. Because the product, the logarithm of a product is the sum of the logarithm, and then everything is fine, and you get this amount of information in bits. The unit is bits for this message A, right? And in fact, if you take the average information, then you get here an expression that some of you might know. It's called the Shannon entropy, and it's the start of classical information theory. And at the same time, it is also a measure for how many bits, so zeros and ones, do you have to send if you compress the message. So in messages, there might be some redundancy and so forth. And this measure really gives you the number of bits that you actually have to send. Okay, so but the information here that is important doesn't depend on the meaning of the message, because meaning is always a difficult concept. And at least in the science, we always point to the humanities, ask them about the meaning. And there is one more thing that I have to tell you about information theory. That is that information can be transferred from one information carrier to the next. For example, I have here a hard drive, and then I have a CPU. This is pretty much what's going on here with my computer. When I press a button, the hard drive might retrieve some information from, sorry, the computer might retrieve some information from the hard drive, send it to my CPU, it's processed, then somehow it's going to some fiber or Ethernet cable, and from there it might go over satellite to Johannesburg. No, maybe not. Maybe it goes via fiber. No, I think it could be satellite even. And in the end, what you see is exactly what I see, namely this presentation, right? So this is the picture of the presentation that I have in front of me, and you will see the same thing because it works in principle without loss. Of course, digitization plays a role in this, and error correction and so forth, but in principle, we can do this without loss. And that's very important, because that means that the physical carrier of the information doesn't play any role in this. It doesn't matter whether it's a hard drive magnetically stored or some electrical signals. It's the same. The physics does not play a role. If you study information theory, you don't need to know about physics. So information can be transferred without loss between different physical carriers. The laws of information processing do not depend on the physical carrier. But what about quantum systems as information carriers? Well, here is a diagram that symbolizes a certain process, and this process is called classical teleportation sometimes. And it works like this. You send a quantum particle, so that is a quantum system, for example, a photon, with some information that it carries, to a measurement apparatus. And the measurement apparatus measures the system, and then it extracts some information, right, from the system. And you use this information. You are allowed to do any measurements that you want. And then you transfer this information using a classical signal to someone else. Maybe you transfer it, maybe I do the experiment here. And then I sent the classical signal to Isaac, and he is in his lab now trying to re-prepare the photon that I have measured here. And then we can ask, can he do that perfectly without loss? If he could do this without loss, quantum information theory would not exist, because it would just be a part of classical information theory. But because you already know, I mean, we have here a discussion forum about quantum technology, it probably exists. In fact, I want to show you that quantum information theory is the basis of all of quantum technology. And therefore, this process cannot work. This is a process that is very lossy. You cannot transfer the information from a quantum system onto a classical system without losing something. So this is news, and this is very interesting. By the way, for those of you that know this machine, I would like to, of course, ask, anyone knows this machine, what kind of machine this is? Sure.
I know.
Oh, you know, Janzi, what is it? Can
It's
you
a
say?
fax machine.
A fax machine. Perfect. Yeah, this is right. It looks a little bit 80s, doesn't it? So the thing is, fax machines, for those that don't know, they work like this. You put a sheet of paper in there, and there is something written, some text maybe, or a picture, and you run it through the machine. The machine will kind of read it like in a copy machine, and then it will send via the telephone line the information to someone else. There is the same machine, and that machine has also a printer, and then it reprints a copy of what you sent. Okay, so this is not possible with quantum systems because if you put them under the scanner, then they lose some information, and what comes out on the other side is not the same, right? So this is the difference, but the fax machine doesn't exist for that reason, but for another reason. So I just want to explain now a little bit. I hope it doesn't take too long. The idea of a quantum system. So if we have a photon, that's elementary excitation of a light wave, and a light wave is an electromagnetic wave. So electromagnetic wave, there is a picture here. You can see that in red is the electric field, and it oscillates along some axis. So it looks already like a wave because something is oscillating. And in time, it is really going up and down in each point. And now the direction of the electric field is called the polarization. Why? Because if you go to some material, and in this material are different charges, then the positive charges are pulled up and the negative charges are pulled down, and therefore it polarizes the thing. Okay, it separates the charges. That's what I want to say. Yeah, and now I have such an electromagnetic wave, and that's all fine, but I want to measure this. Okay, so I have some information in this electromagnetic wave. First of all, what information is that? So what you see here is a superposition of electromagnetic wave where the electric field is going in the y direction, that I call that vertical, and then one in the x direction that is horizontal. And if you do it in parallel, I can't do it so well as on this picture, then you see that in this simulation that you get a circular polarized wave. So superposition of vertical and horizontal gives circular, given that there is a certain phase difference between them. And this is what superposition does. So if I'm able to produce a photon that has these two components, then I can produce the circular polarized light. And if I take other components, then I get also maybe I get diagonally polarized light or something else. And now the trick is that I want to measure this. Okay. And what I want to show you here is that I cannot really measure it on a single photon. But let me first talk about a classical light beam. If I take a classical light beam and put it through a little glass cube that is a polarizing beam splitter, then if it is vertically polarized, it goes straight through. If it is horizontally polarized, it's reflected. And if it's 45 degrees polarized, that means it has two components that go like this, then both detectors click. Okay, so but now you must imagine you have a single photon. That means that is something like an elementary particle. It's not divisible. It is the particle with the smallest energy that you can get for this light, for this frequency of the light. And this comes now, and of course, if it will do the same thing. If it's horizontally, vertically polarized, like an A, then it will be detected in the detector D1 with probability 1. If it's vertically polarized, horizontally polarized, then it will be detected in D2. If it's now polarized where it has both components, a superposition of vertical and horizontal, then what happens? What do you think? Which detector will click? And it's a good question because no one knows which detector will click. At least we cannot predict which detector will click. We can say, if we repeat the measurement many times, Sometimes D1 will click, sometimes D2. Actually, in 50% of the cases, this will happen. And then, then we still don't know what polarization it was, because let's say D1 clicks, then we would think, okay, it was probably vertically polarized, or D2 clicks, then we would think, aha, it was horizontally polarized. But we cannot tell if there are two components, right? So we cannot, in principle, find the state of the polarization of that photon because of the superposition principle, okay? And the idea why only one of the detectors clicks is because there is this energy quantum, and in order to make the detector click, you have to give some energy to the detector. And if you don't have the energy, I mean, if you have only a bit of energy that cannot be divided, it's quantized, then only one of the detectors can click. So there is genuine randomness in this. So I can now send one of two numbers, 0 or 1, or in superposition 0 and 1, only I cannot read it out. And but I can send it, and in that language I could say, it's a superposition 0 plus 1. But if I ask someone 0 plus 1, what is that? Then they will say 1. And that's not what I mean. So I use these strange symbols to say here's two states, and these states are actually, they correspond to vectors, you know. So it's nothing mystical here. And we can detect 0 or 1, but not 0 plus 1. Okay, so I want to show you one more thing here before I start with the teleportation. I'm nearly there. Namely, that you can have entanglement, right? So entanglement means I have two photons and they are somehow entangled. So if the first is in vertical polarization, then the second is in horizontal polarization, and the other way around. Okay. You can do it yourself with your fingers. So this is it. And how do we produce some photons like that? Well, we pump a nonlinear crystal, and the vertically polarized photon, so there comes out a photon pair, and the vertically polarized photons, they come on one cone, and the horizontally polarized photons on the other cone. So if I find a photon here at this location, then I know it's vertically polarized. Here I know it's horizontally polarized. But if it's in the point, if I detect it in the point where they intersect, these cones, then I cannot know what it is, and I get exactly the state. All right. So what can I do with this? Well, I can do fantastic things, and one of them is kind of an entanglement swapping. So here I have a pair of entangled photons. Okay, this EPR is, by the way, Einstein, Podolsky, Rosen. I want to tell you that Einstein was very critical of this thing with entanglement, because he said, look, if I make a measurement on the one side, let's say Isaac and I are sharing such a pair, and he makes a measurement on his side and he gets the result 0, then on my side, I can only get 1. While if he doesn't make the measurement, I can really get 0. I can get 1 or 0, right? So something changes here. And the speed with which it changes is incredibly high. So people have measured how fast such a superposition collapses in an experiment in Geneva. From Geneva to Lausanne, under the Lake of Geneva, there is a fiber cable, and they try to measure it with respect to different inertial frames, and found it must be at least 300 million times faster than the speed of light. And Einstein called this kind of behavior spooky action at a distance, and was absolutely against it. But it doesn't contradict special relativity, because we cannot use it to send signals. Because if I measure here a 1, because you measured a 0 over there, I don't know. If we repeat the experiment, I will measure maybe a 0 because you measure 1 over there. So there is still this randomness that doesn't allow me to distinguish, except you send me a classical signal. I cannot do anything with this. So quantum information theory in general is now something that deals with quantum systems, and quantum information is the state of a quantum system. And superpositions are allowed. So I can store and process 0 and 1 simultaneously. This plays a role in quantum computing. We have seen that in the last talk. Measurement results show real randomness. I told you this. And it cannot be copied or it cannot be teleported. It cannot be transferred into classical information. So the applications of this is quantum computing, simulation of complex systems, and random number generation. And then because it cannot be detected or copied, quantum cryptography. That also was mentioned in the last talk. And the last thing here is entanglement, and that needs teleportation. And I'm going to talk about that in a second. All right. So, yeah, if I have counted correctly, I still have 10 minutes. Is that right? Or more?
Yes,
Can
that's
I?
correct.
That's right. Okay, then maybe I'll just skip over this thing. This is about what we can do in Durban with this quantum computing, and so we do different things here, and we want to commercialize quantum communication. We resell quantum key distribution systems. That's our plan. We get some money and we assemble QKD systems and so forth. You can talk, you can ask me about these things later. We had also a machine to do quantum cryptography at the World Cup, and here is a quantum teleportation experiment about which I will tell you later. But a headline it made: scientists teleport images in Star Trek Discovery. Is of course not the same, right? But this is what the press does with it. This is a student of mine. This is a small component that goes into a quantum random number generation chip that goes into a cell phone uh, uh, of the Samsung kind. Okay, here is the classical teleportation again. I want to talk in the last 10 minutes about quantum teleportation. So classical teleportation was this process, and we saw it's not possible. So now it will be absolutely surprising for those that don't know, and I'm sure it would have been surprising for the founding fathers of quantum mechanics even, that we can do the following process. It's called quantum teleportation. And how does it work? Well, the input and output is the same as in this impossible scheme, but here it really works. So I can send a photon in here. I make a measurement together with a photon. I measure two systems at the same time. This is a system from here coming that is entangled with the photon on this side. And then I do a transformation of the photon on this side that depends on the measurement result. But the measurement result doesn't tell me anything about the state of the system that comes in here. So this is totally independent of the state that comes in. It's one of four measurement results, and then this really works. I can reproduce the state of the photon that was incoming here on the remote side. So I could teleport the polarization of a photon from from me to you, even though no information about the photon polarization is traveling in between, right? It's not really in this entangled state. It's not in the classical signal. So this is quite amazing. And here I must thank Andrew, because 10 years ago, or so, no, it's actually already 20 years ago, nearly, he pointed out to me that there are people that work with orbital angular momentum of light. So that is these curved light fronts. And they can be produced by some spiral faceplate, for example, and they look like this. The intensity looks like this, but it has different winding numbers. So in principle, you can have orbital angular momentum of +1 in some units, or +2 or +3, or many, many, many. And then you have not only two polarization states like vertical and horizontal, but many. Okay. And that's, of course, amazing, because with that, we can do things. And here is an image that I also got from Andrew, which shows nonlinear optics. So in nonlinear optics, this is something we want to use now for this teleportation. In nonlinear optics, I can send in two fields from the left here of red light, and then I get a blue field that has the electric field is the product of these electric fields pointwise. So in each point, I multiply the values, let's say, of the magnitude of the field vector there, and average field vector, and then I get this thing here out, all right? So this thing here can do multiplication. Can it also do division? That's a question. I can tell you this much, that if you send this light beam the other way around, so you start with a blue light beam, send it in, then you get exactly these two out, and all products that lead to the same product. So all factors, sorry, that lead to the same product. So maybe one should think about factorization again. But this is just a side remark, because we will use this now in the following scheme to teleport things. So what you see here is a light beam that comes into such a nonlinear crystal, and then two photons come out. They are entangled, so this is this entanglement resource. And then there is another light beam that is measured together with this thing. And how is it measured? Well, it first goes through a nonlinear crystal. In the nonlinear crystal, there is this multiplication of electric fields, and then it is measured here in the same state. So there is a filter here that you can't see, in the same state as the pump that came in here, right? And then somehow, by the logics of this quantum teleportation, if the same thing comes out, goes in here as comes out here, then what goes in here must also come out here. Isn't that amazing? So I want to show this. Also, again, I thank Andrew for the slide. I want to show you how this works. So let's say L equal to 0 goes into the one nonlinear crystal, and out of the other nonlinear crystal, you get L equal to 0. So you make a filter there so that these two components are the same. Then this means that in order to add up to 0, the orbital angular momentum here in the red beam must be +1. +1 plus -1 gives 0. Okay, and then this whole thing works. Don't be irritated that I say it's a multiplication. These orbital angular momentums, they appear in the exponent. So if you multiply two powers, then the exponents add. So it really adds to 0. So what we need here is L equal to 1 there. And because there is angular momentum conservation on this side, this last thing, if this is L equal to 1, the total angular momentum must L equal to -1, and then I get this thing out. Right? So what I send in is L equal to -1. What I get out is L equal to -1. And that basically means, yeah, what does that mean? That means that if I take a superposition of not only L equal to -1, but L equal to 1 and L equal to -3 and many other modes, and these form a basis for all modes, then I can actually do that in parallel, and I will get the superposition out. So if you put a picture of yourself in here, you will get that picture teleported to Johannesburg or to Durban, depends where you want it. Okay, so this is quite fun, I think. And this experiment was the first experiment that was done in this, and was done in Andrew's labs. And Isaac was also involved in this, and many other people, also international people. And here are the results. And it basically means that the fidelity with which this image is transferred to the other side is kind of higher than the classical limit, higher than the limit of this classical teleportation. Right? So this is my main message. And now whatever comes in the last 3 minutes is kind of a bonus. And what I want to talk about is how can we generalize the scheme? And we have kind of developed together with collaborators Steph Rue and Tanita Permaul, and a postdoc from India, Arijit. We have developed a scheme how we can actually teleport many modes at the same time, but we want to teleport now really actually full laser beam. So we want to have bright states of light to teleport. In the example that I showed you before, this was just single photons. In the end, a single photon came out. Here I want to have really a visible image that I teleport. And one way to do that, we know how to teleport a single mode. If I had many of these single modes separately, and I would first separate them, this is a mode separator, and then I would mix them, this is a mode mixer, then I would get out the same thing again. So it's similar to if you shine white light in, you can put it into its colors using a diffraction grating, or if you put in such a petal mode, then you can write it as a superposition of two of these orbital angular momentum modes. Okay, and so we put in the petal mode, and we could teleport now each of the modes, put it together, and then we would get the petal mode on the other side. All right, here is some calculation that shows that in each point or in each mode, so that the mode, the state of the mode, that is like the state of a laser beam, can be seen as little small laser beams that have some kind of diffraction of the intensity. So to go further, we can do the same thing with pixel mode. So instead of orbital angular momentum, we now divide the thing in pixels. I'm finished in one moment. Just give me 1 second. The pixels are small pixels now. If they are small enough, then the light field is constant on them, and then I can really do this thing in one go. So I don't need this mode sorter, because each pixel of the light field of a transversal mode is already kind of sorted by itself. And here's some calculation. Here is the full scheme. Unfortunately, I cannot show you. I just want to show you that the fidelity in the end is very high. So you see here a very high region where this perfectly works, fidelity one. And this was with noise and with a full calculation of the down conversion process and so forth. So if you like that, then please contact me and we can talk about it. This is something else. I want to point out that we have a Center for Quantum Computing and Technology that we just started. In fact, the launch is next week. And we have a Quantum Africa, so African Quantum Alliance, where we want to build a quantum computer together with other African people from other African countries in order to use this chance of this opportunity of building an industry. Okay, so this is all I have to say. Thank you very much for your attention and for letting me speak to the end.